second talk for today is Kayvan Sadeghi, and he will be talking about axiomatization of interventional probability distributions.
Hello. Yeah, thanks for the invitation, particularly Codina, who is not here. So yeah, so this is really not related to coding theory at all, but there is some, and there's not much real probability theory in there, but it is related to probability, I guess, as you'll see. So the idea is to differentiate intervention and observation. So this is what people did in the 80s, like Judah Pearl, and then some crowd in CMU, you might know them as like Clark Gilmore, Peter Spiritus, etc. And I mean, in the philosophy, it was kind of always known that intervention and observation are two different things, but they somehow formalized it in the 80s. So one simple example is that, okay, you can observe that there is a correlation between smoking and the color of the teeth, right? But no matter how much you go and whiten or blacken somebody's teeth, their smoking habit probably wouldn't change. Whereas if you force somebody to smoke, I mean, might be not quite ethical, but if you do that, then the color of their teeth would change. Then that's, so doing things infer the causal relationship. So now you can infer that the actual causal direction is from smoking to color of the teeth and not vice versa, right? So that's sort of the idea of the difference between observation and intervention. So seeing something or doing something. So that's how you can infer causal relationships. There's a counterfactual approach to causality that we're not discussing here. There is also, you might have seen structure causal models. Sometimes they call them structure equation models. So that's a sort of semi-parametric sort of model. So there are assumptions on the relationship between random variables. And that is not our assumption here. So I would say the majority of the causal inference work for intervention is based on these structure causal models. But one point that we are making here is that we don't need to assume that. We will see that, in fact, it is sort of, STMs are kind of embedded in this setting. So these are somehow consistent with the setting of structure causal models, but we don't need to assume there is a structure causal model. So you might have heard of Pearl's do calculus. So in essence, this is very similar. So we are trying to define do as Pearl does, but again, there he assumes structure causal models, and again, that's not our focus. So the question is, what's an intervention? I mean, it's a philosophical question, and we don't answer it very precisely here, but there are generally two types of interventions. One is the what we call the hard intervention, where if you intervene, it kills any cause it has, right? So that's quite intuitive, right? So if you force something to be something, then it doesn't matter what causes it had previously, right? But I mean, in some applications, the intervention might be soft. So you might intervene and still some other variables affect this variable, right? But what we are considering here is hard intervention. So it kills all other causes, as you'll see in the theory. And the other thing is, so our interventions here are stochastic. So sometimes there is an intervention called atomic intervention, and it forces the variable to be an exact value. It puts all the mass on one point for that variable. But here our intervention is stochastic. We basically intervene and give some distribution to the variable we intervene on. Okay? So you will see this a little bit more clearly. So let's first discuss structural causal models, because this is the main model. But as I said, we don't assume this in this talk. But this is sort of the main setting in the literature. So you have a collection of random variables, and they assume there's a true causal graph. Again, that's not something we assume, but that's what the setting there. So they assume there's a graph G. let's call the node set V, and okay, the graph could have two types of edges. It can have a directed edge, we call it an arrow, or a bidirected one, we call it an arc. And an arrow somehow captures direct cause, whatever that means. And this bidirected thing indicates the existence of a latent variable. We'll see an example of that. So it's basically a variable that causes these two endpoints. And then if that variable is latent, unobserved, then you indicate that using this. Okay, so what's an SCM? A structured causal model basically is a system of equations. So for each of the variables here, that is equal to a function of certain variables and a noise. And those variables are those that appear as the parents in the graph, the variables that are the parents in the graph. Should I draw it? Or, I mean, I think I have an example, so perhaps you'll see. But I guess you understand what I mean. So basically, node J is a parent of I if there's an arrow from J to I, right? So then you can define the set of parents of I. So all nodes that are parents of I, okay? And epsilon i's here are the noises. So the point is, if there is no arc, if there is no such thing, then all these epsilon i's are jointly independent. That's the assumption, right? But these arcs make these epsilon i's dependent. Okay, the noise is dependent. So this is an example of that. Let's say this is your graph. Okay, so this is the true causal graph, whatever that means. And then this could be this is an SCM, right? This is the general form of the SCM here. So x4 is just a noise epsilon 4, x3 is just a noise epsilon 3, x2 is a function of x4 because it's only parent and some noise, and x1 is a function of x3 is only parents and some noise, and because there is an arc here, epsilon 1 and epsilon 2 are dependent. Okay, and other epsilons are independent. And what is this really? If you think of a latent variable x5, then the real picture was this, right? And that led to this because 5 is latent. Somehow this led to this arc. So that's the sort of setting. Any questions on SCM?
Connection with like Markovian graph and the kind of Markov structure, is that related to?
It is related. Yeah, we will talk about Markov structure soon. Yeah, it is. Yeah, you will see that the joint distribution is Markovian to this. That's a no result to this graph. But in both. Yeah, but you will see it more precisely. Any other? Okay, so what is an intervention on SCM? How did they define intervention on SCM? So basically, and again, we don't do atomic intervention, but stochastic intervention. So let's say you want to intervene on xi. You basically put xi in this setting. You replace the equation you had for xi with simply some distribution x tilde I. So that's what you do. So how does this work then? It basically kills this arrow when you intervene on 1. Let's say you're intervening on x1. What it does in the graph, it kills the arrow, and it also kills this bidirected thing, because if you look at here, it's more clear why this connection is killed, right? Because you kill this and you kill this, right? And then how does the equation look like? The system of equations look like? So x4 would be epsilon 4, x3 would be simply epsilon 3, x2 is still a function of x4 and the noise, but now x1 is being intervened on, is being replaced by simply what you force it to be, right? This x1 tilde. Yeah, go ahead.
Shouldn't x2 depend on x1?
No, because here you see that the dependence of x1 and x2 is through this latent variable x5. And when you intervene on x1, you're killing this relationship.
You're killing the left edge.
The thing between 5 and 1, yes, which kills any connection between 1 and 2. So in a sense, when you intervene, you want to kill the arcs as well, not only arrows, right? So arcs that are connected to the node you intervene on will be killed, right? Okay, any questions? No? Okay, so now let's talk about the objective of the talk. So basically these all rely on the theory of graphical models. So we need to give some basic theory of graphical models, and then this is the main thing we want to do. We want to sort of axiomatize families of probability distributions to be considered interventional distributions. So we want to sort of say which, if you give me a family of distributions, when they could be considered interventional distributions. And we'll have a theory on that. So what's the advantage of this setting that we are trying to propose? First of all, they do not assume structural causal. So you do not rely on any modeling assumptions. And secondly, as you will see in the theory, it relies only on interventions on single variables. So in SCMs, you might intervene on a couple of variables. So this could be extended if you intervene on like 1 and 2 or something. But here we only rely on single interventions. And most importantly, it does not assume the existence of an underlying true causal graph. So SCMs assume there exists a true causal graph, and then based on that, you write the system. Here, we don't assume there's a causal graph. We start with just these probability distributions and try to construct this causal graph. So that's the thing. And it is more general because it allows for causal cycles. So it could be cyclic, although there are theories for SCMs that work with cycles, but they're not really nice. They're quite hard to work with, as you will see. Okay. So, okay, and then we define the causal graph, and we define some theory related to the causal graph we construct, and we show that a large class of SCMs are basically satisfy the theory here. So SCM is kind of the theory is embedded within this larger theory. Oh, did I say it's a joint work with theory, by the way? Sorry. I just remembered. Yeah, so and it's appearing in Biometrica. It's not out, is it? I don't think so. It's in the website, but not with, page numbers and things yet. Yeah. Okay. So let's discuss graphical models briefly. So what's the idea? Do you know graphical models or like zero? Okay. Ooh, okay. So Frank knows, I know. Okay. So I'll discuss very briefly. So you know what conditional independence is, of course. Let's assume there is a density, but you can define it without densities. And okay, X is independent of Y given Z if this factorizes. And usually if you have this random vector XV, then usually in graphical models, we simply say A is independent of B given C for an A, B, C are disjoint subsets of B. Instead of saying X sub A is independent of X sub B given X sub C, we usually just write A independent of B given C, right? That's a short notation. So graphical models use graphs to somehow represent these conditional independent structures among random variables. So what are the nodes is exactly what you had in the SCM setting. So nodes represent random variables. So you would have V nodes, right? X1 to X size of V. And edges indicate some type of conditional dependence among these random variables. So the difference with these causal graphs is that here, this graph is only like an edge, only represents dependencies, conditional dependencies somehow between these random variables. Whereas in that SCM setting, the edges have some causal meaning associated to them. So you know that, of course, that these are not the same. Okay, so I mean, in general, in graphical models, there are different types of edges that people discuss with different independence meanings. There are these two types of edges we discuss, and then there is this undirected edge that we don't use in this talk. I might very briefly say what it is here, but okay. So the type of graph we allow here has basically these arcs and these arrows. We allow cycles, and we allow arrows in two different directions. So if you want to interpret that, you can say this causes this and that causes that, right? But we do not allow something called a bow, which is an arc and an arrow between two nodes. That we should exclude. We have actually some theory to deal with some cases, but we're not discussing it here. And I might, if I have time, I explain why we are excluding this. Okay? Just some simple definitions. So you saw the definition of parent. That could be extended to ancestors, right? So we say I is an ancestor of J. If I is a parent of something and that thing is a parent of something else, and they go all the way to J. So parents of parents of parents. I mean, that'd be ancestors. And we also allow for directed cycles, i.e. I goes all the way and goes back to I, right? So a cycle all in one direction. So we allow for those, okay? So the largest class of graphs we discuss here is called ancestral graphs. So basically they're graphs, no, it's not, actually it's not true in general for our setting, but I think I focus mostly on ancestral graphs here. But anything is much more general, right? So what are ancestral graphs? There are graphs with without directed cycles. And if you have an arc, one endpoint is not an anterior of the other. So there is no such. So you don't have these. But as I said, the theory is much more than ancestral graphs. But I sometimes work simply on ancestral graphs, which is easier. And there is no such thing. So you exclude these types of graphs. Okay? So that will give ancestral graphs. Okay, so most theory on SCMs is for DAGs, simply graphs with only, so directed acyclic graphs, simply graphs with only arrows and no cycles. That's the most theory, but there are some theory for ancestral graphs. There is some theory for graphs with cycles as well, but it doesn't work well because there are strong functional relationships in the SCMs, right? So if you have a cycle, you need solvability assumptions between these functions. And that's not trivial at all. Okay, so SCMs really don't work well with cycles. Okay, any questions? Okay, so then you want to define, you want to connect probability distributions and graphs in graphical models. So what's the idea? You define separation on graphs, and then you connect conditional independence and separation together. That's how you connect probability distribution and the graph. Okay, so what is, I'm not going to explain how separation exactly works in the graphs. It's a little bit technical for somebody who hasn't seen it. But basically the idea is that you take some nodes and some other nodes and some third subset of nodes, and you say A is separated from B given C using some criteria. Okay? So in undirected graphs that we do not discuss here, this is very intuitive, this separation. So basically, it says that if you take the nodes in the conditioning sets out, then the other two get disconnected. So here, for example, in this undirected graph, if I take, for example, J and L out, then I gets disconnected from K, right? Therefore, we say I separated from K given J and L. And we use this notation for separation and this notation for probabilities or for independence, okay? So this means independence in distribution, this means separation in graphs, okay? For these purely bidirected graphs, it's kind of dual to this. So if you have I and K that are not somehow connected, then they are sort of marginally independent always, or separated, right? So it's kind of dual to this. So for example, it's very obvious. If you take everything out, then these will get separated, right? So these graphs, if there is no edge between something, they're always separated given all other nodes, right? Of course, if you take all other nodes out, they get disconnected, right? Here, a missing edge, so to speak, somehow corresponds to marginal separation. Okay, but as I said, you don't need to worry about it. And for this, there is something called d-separation that reads off these types of separations that is implied, by the graph, okay? But I'm not going to explain d-separation or the more complicated ones. And then for the more complicated types of graphs, there is still separation criteria that decide what is separated from what given what, okay? Any questions? No? Okay, then now we want to connect probability distribution P and graph G. So how do we connect them? We say, so one connection is this. We say that if they are separate, A is separated from B given C in the graph, then A is independent from B given C in the probability distribution. So it's a one-directional thing. And that is what is called the global Markov property. Or you can simply say the distribution is Markovian to the graph. P is Markovian to G. If separation in the graph implies independence in the probability distribution. So that sort of connects P and G, right? So a very essential result for SCMs that basically all the theory of SCMs is based on is this theorem that joint distribution of an SCM is Markovian to its associated graph. So that comes from the setting of the SCM, right? So you have this system of equations. You can, of course, write the joint density. If it's defined, then it will be Markovian to this graph, that joint distribution. Okay? So for DAGs, it's very known. For ancestral graphs, we showed it, and there are even results even for directed graphs. So when you have cyclic graphs, it is true. Okay, so that's the main result for SCMs. Okay, so there is some other type of Markov property, which we call pairwise Markov property. So what's the pairwise Markov property? We say that P satisfies the pairwise Markov property if when you have a missing edge, when I and J are not adjacent, then you have I independent of J given the ancestors of I and J. So by this, I mean the union of the two ancestors. Right? So here, so if I go back to this example, for example, for this type of graph, you see that the pairwise Markov property implies this, for example, right? Because there is no edge between I and K, right? And ancestors are somehow these two, okay, whatever that means. And then is I and K are separate, independent. Now this holds in probability distribution actually. So for this graph, there is no ancestor for I and K, so it's empty. Therefore, pairwise Markov property here implies I is independent of K. Okay, does that make sense? Yeah. So you can think of this pairwise Markov property as a basis for this global Markov property. The global Markov property implies a lot of independent statements, right? Of form A independent of B given C. Pairwise Markov property only implies sort of pairwise independencies, like I independent of J given C. But then why do I call it a basis? Because of the equivalence of Markov properties. I'll explain a little bit later, but just a couple of more definitions and then we're done with the definitions. So there is another thing that we call maximal graphs, and it means that by adding an edge to the graph, the separation changes. So it's equivalent to saying if you have a missing edge between two nodes, that has to correspond to some separation. For the simple types of graphs, that's always true, but when your graph is more complicated, that is actually not always true. So we will work for maximal graphs, generally speaking. And then, okay, and the largest type of separation we have is called sigma separation. And this is the last definition. So an inseparable pair of nodes is if you have a non-adjacent pair of nodes that can never be separated, right? If you have two nodes not adjacent and there is no separation for them, we call them inseparable nodes. Okay? But the largest type of separation we talk about in the literature is called sigma separation. But I haven't defined it anyway. But you know, that's the separation that gives you these this set of separated, you know, conditional separations in graphs. Okay, so when are this pairwise Markov property and the global Markov property equivalent? So it's easy to see that global Markov property always satisfies pairwise Markov property. So if you have this separation criteria, that implies this pairwise Markov property. For example, if we go back to this undirected one, although we don't work on undirected graphs, but it's easier to explain it. So we said that here pairwise Markov property is a missing edge, means separation given all other nodes. So i.e. pairwise Markov property implies this, right? So global Markov property says if you remove nodes, they become disconnected. So you see immediately that global Markov property implies pairwise Markov property, because if you remove all other nodes other than those two, it makes them disconnected, right? So one direction is kind of trivial, but the other direction holds under two assumptions. So if your probability distribution satisfies these two conditions that we call intersection and composition, then if you have pairwise Markov properties, you can construct all the global Markov stuff, all the statements that come from global Markov property. That's why I said you can think of pairwise Markov property statements as the basis for this whole separation independence model, right? You start with these pairwise ones, you apply these two conditions, and then you can generate all the statements that are implied by the global Markov property. I mean, these you do not need to understand completely. Intersection is very easy. If you have a density, and if density is always positive, this is always satisfied. So that's a sufficient condition for intersection. So intersection is not really a strong assumption. Composition is stronger. Of course, you know, a first course probability is like you have I, like think of C as empty. Then I independent of J and I independent of K does not imply I independent of J and K, right? So that's an instance of composition not being satisfied, right? So composition is sort of a generalization of that for conditional independence, right? So this is slightly more restrictive, the composition property. Any questions on the theorem?
Should I be thinking that IDNC is always individual random variables? Or
they're subsets, but disjoint. Exactly. So A, B, and C are subsets of V, the whole set, but they're disjoint. Yeah, but they're arbitrary. Any other questions? Okay, now this is so that's the old theory that I haven't said anything that we've done. So this is basically what we've done in this paper. So we would like to define the interventional family of distributions. Okay. So we define a family of distributions. So this has basically V or size of V joint distributions in there. So there are like n joint distributions in there. And we call them P sub do I. Okay, so for each node, let's say, or for each member of V, you have a joint distribution. And you should think of these as intervention on I. So the distribution, the joint distribution you get after you've intervened on I. So these are really your interventional distributions, okay? But the point is they all are defined over the same state space, right? So that's because you need, of course, they're working on the same object, right, at the end of the day. Okay. So as I said, P-I you can think of as interventional distribution after intervening on some variable xi, but a joint one. So let's say this family of distribution is given to you that we are hoping that is interventional. So we need to put some assumptions on that so that it works in a reasonable manner. But before that, we want to define cause, the concept of cause from this interventional family. Okay? So what is really a cause now? If we take K, a node, so we say cause of K is the set of all i's such that when you intervene on I, so if you look at this interventional distribution on I, so P do I and K are dependent, are marginally dependent. So it's quite intuitive, right? So I is the cause of K. When you intervene on I is still dependent on K, right? So then it means that I causes K, right? So you put all these things in a set, and that set is the set of causes of K, right? So by convention, we say I is not equal to K. So we don't let K be cause of K, okay? And this is compatible with the stochastic interventional axioms. That's pretty much how they do it, okay? Okay. So let's look at our first axiom that we need so that the theory works. We expect this family to be a transitive interventional family. So basically, this is our main axiom. So our main axiom is that we expect cause to act transitively, so cause to be transitive. So if I is a cause of J and J is a cause of K, then we expect I to be a cause of K as an axiom. Okay. And of course, if you look at this definition, that puts a lot of constraints on these P do I's. So this axiom somehow connects these different P do I's, right? Because here cause depends on different P do I's. So when you define the set of cause, you're going through, you need to look at several of these P do I's, right? So here is P do I, and I is changing, right? Is varying, right? So this axiom connects somehow P do I's together in a nice manner. Although it's quite intuitive, philosophers have come up with cases where cause is not transitive, right? So you can come up with cases, and it's not really that difficult, that I causes J, J causes K, but I somehow doesn't cause K, right? But we would argue this is a relatively intuitive, axiom to have, right? Okay. So what's a causal cycle? Basically, we call S a causal cycle, if you take I and K, K is in cause I and I is in cause K for every two members of the cycle, right? So that's how we define a causal cycle. And this, of course, sort of induces an ordering for these let's call them nodes, right? Or it's actually a pre-ordering. So I is less than K if and only if K is a cause of K, and I is not a cause of K. So this is strictly less, right? And then we say they're somehow in the same equivalence class if K is in cause of I and I is in cause of K, right? So they belong in the same causal cycle. Okay? Any questions on the definition of cause, etc.? Okay. Okay, but we still haven't defined a graph. We have our family of probability distributions. We still don't have a causal graph. We would like to define a causal graph. So in order to do that, we want to define the concept of direct cause as opposed to just cause. So what is a direct cause? So we define it in this manner. Okay, it's a little bit, it requires something we called intervened cause of K. But if it's a little bit difficult for you to grasp this, you can simply think of this as cause of K. For simpler types of graphs, this is simply cause of K, right? So don't worry about this too much. Just think of this as cause of K. So D cause is the set of nodes, or subscript if you want to call them, or set of, if you think of this as xk, then this is the set of xi's variables, such that I is in cause K. So I is already a cause, but in addition to that, when you intervene on I is still dependent on K, conditionally given all other, let's say, causes, although this is, as I said, slightly different. So if you intervene on I and condition on all other causes, if I and K are still dependent, then there is some type of direct causal relationship between them intuitively, right? So that's how you're defining the concept of direct cause, right? So if you know that your causal graph is ancestral, although we still haven't defined this causal graph, but in principle, if that's an assumption, then this I cause is simply cause. So that's, and so as I said, it is, maybe I have an example that explains what it is, but don't worry too much about it. So then this condition is simply I dependent on K given cause of K when you intervene on I. So when you look at this probability distribution do I, P do I, right? So as you see, cause is a universal concept. So if you look at definition of cause, right, it doesn't matter how large your system of variables is, you can define this in the same manner, right? So this is invariant under that. Whereas I cause clearly depends on the system, depends on other variables. And that makes absolute sense, right? Because if you have something, a cause of something, you can always, or in many cases, you can introduce a variable between these two, right? So if you have some sort of direct cause, right, whatever that means, so, and then you can always define some variable that kind of comes in between, right? So the concept of direct cause depends on other variables you consider in the system. But the concept of cause is somehow universal, right? It doesn't depend. And now I guess you can see how I want to define the graph, right? I guess you can guess how we want to define this graph, right? Well, before that, let's look at an SCM case. As I said, SCMs are embedded in this theory, so we can have SCMs as our examples. Okay, so let's say we have a well-behaved SCM, whatever that means, and let's say this is the graph, or this is the true causal graph. So here you see that cause of K is J, is also I, and it's also L. So there's a causal relationship here, right? So I cause is basically intervened cause sub I of K. So this basically means you cut you're intervening on I in a sense. So you cut parents of I, so you're basically cutting this, right? So L is no longer in this set. So so it would be only J and I because you've cut this edge, right? So that's how you define I cause. And okay, so let's say, so we have, if you do J, kind of cut this, you see that J and K are still connected even given I. And also if you do I, so you cut this, oops, sorry. I and K are dependent given J through this path. So in a sense, you see that d cos of K is simply J. That's how we define d cos. And you see in the graph, d cos or direct cos is simply what comes as a parent of that node, as you expect, right? So that gives us an idea how we want to define our causal graph, right? Okay, so let's define our causal graph. First, we define something called causal structure. That's basically if you have a d cos, you put an arrow from. So if K is a d cos of J, you put an arrow from K to J to indicate that's a d cos, right? So far you've generated a directed, so a graph only with directed edges, right? So that's what we call a causal structure. And then an I-intervened causal structure is, as we've done many times, you just remove parents of I to somehow intervene on I. So that would be the I-intervened causal structure. Okay, and in order to define I-intervened causal graph, you would need to add these latent variable cases, right? So these arcs, so to speak, right? So how do we add these arcs? So you look at places where I and J are not adjacent already, okay? And then you look at this. Like, let's say J and K are not adjacent in this causal structure. You do I for other I's, and if they're dependent given their common cause, then you would like to put an arc, right? So in a sense, it is telling you that, okay, I'm intervening somewhere else in the graph, right? And I'm conditioning on all causes of J and K, but they're somehow still dependent, right? So intuitively, it means that there was some latent thing that, and we know that they're not direct causes of each other as well, right? Because there is no arrow between them. So you're looking at two nodes, no arrow between them, no direct causal relationship. You've conditioned on all causes of both, and you in some interventional distribution somewhere else, and they're still dependent. So there must have been a sort of a latent variable that causes it. And that's when you put this arc, right? So now you've generated what we call the I-intervened graph. Okay, and then the causal graph is, okay, you put this when this holds for every I. So if you intervene on every I other than J and K, and this dependence holds, then you put that in the causal graph. Now you have your causal graph. So it's basically your causal structure plus these arcs, right? Okay. So that is what we call G of this P-do. So you've given me the family of interventional distributions. I've outputted a graph, right? And then you can define G sub I, which is kind of intervened causal graph of I. And you know how you do it. You cut parents and arcs of I, as we did many times. Okay, so from this family of distribution, now we have defined a graph. So what are the results of these axioms? One important, the first but important result, which is surprisingly not that trivial to prove, is that, okay, I generated this graph and I know the set of causes. We have this relationship. So I is an ancestor of K in the graph, in the causal graph, if and only if I is indeed a cause of K in this family P-do. So they correspond well, but of course it's under the axiom we had that cause is transitive. Okay, so the graph now works reasonably in a reasonable fashion, right? Okay, one advantage of this setting, just one, is that now you can generate cycles quite easily, right? Whereas in STMs, as we said, you need these functional relationship, you need some solvability among these functions, which is not trivial at all. Also, we can show that this causal graph leads to, is always this this bowless directed mixed graph that I defined at the beginning. So that's the structure you get. So it won't lead to bows. That's pretty obvious because we only put R. So if you remember, bows were these, right? Bows were these. And you never get these because you only put these when this is not there already. That's how you put them, right? Okay. So but the main theorem is that, okay, if you look at one distribution P do I, so the intervened distribution of I, and let's say you have the composition property, then I is independent of K given all causes of K in this P do I. So this looks like because now K is like ancestor. So this looks like that pairwise Markov property we had, right? And then that leads to the global Markov property, right? And which leads to our main theorem, which says that, okay, you have your family of interventional distributions, and that family is transitive, causes transitive as an assumption. And let's say this P do I satisfies intersection and composition property. So that's another assumption we need. Then this P do I is Markovian to the I intervened graph GI of P do. So you have this global Markov property between the interventional distribution of P intervened on I and the graph intervened on I. Okay? And one last result I try to explain. Okay, let's do the example, then I'll explain the last result. So all these different edges can actually occur in a setting. So let's think of, for example, x1 and x2 dependent in the observational distribution you had in P. In this is just the normal P, right? I mean, not Gaussian, but like ordinary P we were discussing, right? Okay, then you can think of these two, like two different settings, x1 and x2 being equal to phi x1 and some noise, or x1, which is some noise of x2 and v, and x2. And let's say u and v uniform noise, okay? So how can we define different interventional families? So one idea is that, okay, we say P do 1 of phi, right? We look at this phi, and we define the interventional distribution of 1 here, and we define interventional distribution on 2 using this. Or we can define both of these using this setting, or we can take P do 1 of phi and P do of psi. We take one from here, one from here. Okay, so in this setting, you place an arrow from one direction to the other, clearly. In this setting, you put the arrow the other direction. In this setting, you put an arrow this way and an arrow that way, so you get a causal cycle. So you see, even with two random variables that are dependent, you can define different interventional families that lead to all these causal structures. And there is a way to even do this arc thing. Okay, let's keep that for now, okay? So all these graphs could potentially occur under this setting. Okay, so my last theorem is, okay, so far we only discussed about P do I. So we showed that only using interventional probabilities, you can generate a causal graph. You really do not need any observational probability to generate causal graph. So causal graph is all about interventions. It has nothing to do with the baseline distribution or the observation. But okay, if we have an observed P, when does it act reasonably with this setting? Then you need an axiom that we call P is observable. Okay, so this family P do is observable with respect to the underlying distribution P if these two axioms hold. So when you have independence in conditional independence, given all the joint causes in P do I, then you have that independence in P. And okay, you need to look at two of them because this is J, K, and I are disjoint. Here, I is this I. But that's basically the idea, right? That somehow independencies are preserved between, or conditional independencies given joint causes are somehow preserved between P do I and P. And if you have this as an axiom, then you can also say that, okay, if you have your family, interventional family, again, transitive, that is transitive, again, you have intersection and composition property, then this, if you have this as well, then this P here is actually Markovian to the causal graph. So we have this Markov property of P to G. Okay, I think I just go to the summary. But basically, what I also showed here that I don't have time to discuss is that SCMs, under some reasonable assumptions, indeed are embedded in the setting, satisfy all these. Okay, so that's the idea. So this is sort of a generalization of SCMs. Okay, so what have we done? So we have provided a general theory of causality. We do not need to make use of any modeling assumption like structured causal models. We only rely on, as you saw, we only relied on single intervention on single variables. All our setting required only P do I, not P do a set, right? So it induces most cases of graphs. It can detect latent variables and it can detect causal cycles. And it does not assume the existence of underlying causal graph. Causal graph is a byproduct of our theory, right? We did not start with any causal graph. So what we did, we defined the concept of cause and then the direct cause. And from the concept of direct cause, we generated the causal graph, right? And then we provided axioms such that, such that this Markov property of P do I to the intervened causal graph holds. And also, if you have an underlying distribution, the Markov property of P and the actual causal graph holds. Okay? And in the paper, we have something else called quantifiable observational. And that is for measuring causal effects. So the axiom really relates. I might have just the formula I just showed. So it's something like this, the axiom. So it's actually relates the actual probability distributions, right? Because so far what we did, we've only worked with independencies. It was only independence structure that we care. But in quantifiable setting, there is some constraints on the actual probability distributions, right? And under those, we can actually measure these causal effects. Okay, so far we sort of identified causal effects, but under this additional axiom, you can actually measure these causal effects. Okay, and again in the we showed that the interventional and observational distributions are Markovian to intervened causal graph and the causal graph respectively. And that is really what the theory of SCM relies on. So having this theorem, really you can apply the theory of SCM. So the theory of SCM follows from there. And in the paper we showed that the natural SCMs are embedded in setting. So I should say there are certain strange cases, they're very unusual, that single intervention is not sufficient to capture the whole thing. So we have identified in the paper some cases where you require multiple intervention. With single intervention, your causal graph doesn't completely make sense. So it makes some errors in detecting the causal relationship. And we have identified those cases. Okay, I think this is the end of it. Thank you very much.
Questions?
So, just trying to understand how the theory you've designed, the conditions that you need to check. How do you imagine people get into the graph and then checking those conditions?
So well, I mean, we haven't really done application here, but let's say if you have some interventional studies, right, intervening on one variable, then you can test these conditional independencies after intervention, right? And from that, you can obtain the graph. But this is completely theoretical because, of course, in no study you intervene on every single variable in your. So this is of theoretical nature. But yeah, but there are already methods that say, okay, you can sort of intervene only on these variables and make inference about your graph, right, based on certain interventions you have. Or you can, or maybe a future work could be which variables you really need to intervene on in order to sort of identify this graph to a good extent that you need, etc. Okay. Right? But this is really of theoretical nature, and it says the intervention is on all variables.
In an example, these are things that people are going to have to sort of assume are true in order to.
Yeah, so somehow these axioms are really needed. That's what we are trying to say. And perhaps these conditions need to be checked if somebody is claiming that there is causal relationship in the system.
Another question? Someone? So I do have a question. At some point, you assumed that you didn't allow the graph latent variables plus, so both.
Yeah, so this thing, I guess.
Plus another argument.
Yeah.
Yeah, I didn't. What was the point of that?
Okay, yeah. So if you think about, if you only have access to interventions, okay, in any setting you think in the world, no matter if it's our setting or not, there is no way to distinguish between these two, okay? If you have only two variables. But actually, a part of our paper that the reviewers kind of asked us to add is whether there is a way to infer such things when you have more variables. In certain cases, I would argue some reasonable cases, but not every case, there are methods to detect these using some additional assumptions. But that relies on observed distribution. So only using interventional distribution is very hard to detect these. So you need some sort of observable distributions to do that. So I don't say if you only have interventional distribution, this is not a weakness because it's impossible anyway. But of course, in most statistical studies, there is the underlying probability distribution that people have access to rather than the interventional distributions.
Any other question? Okay, let's thank the speaker.
Thank you.